Pleasant day. Today, we're gonna solve two problems from the book Fundamentals of Analytical Chemistry in chapter 8, numbers 40, 20, 24, and 25. So what will be the contents of this presentation? First is our objectives. Next will be the procedure that we will be using in solving the problem and arriving at the data and calculations. Next is our first problem. Next would be the calculations for the first problem, the Excel spreadsheet and graph for the first problem. The next problem, calculations for the second problem, Excel spreadsheet and graph for the second problem, the results and analysis of both problems, and finally our conclusions. Conclusion: if we are able to meet the objectives. Objectives. First objective is to find the relationship. To identify the relationship of the given values of concentration and absorbance values or emission intensities. Second, the data calculations. To find mean absorbance values or emission intensities, standard deviation, least squares best light, calibration sensitivity, analytical sensitivity, detection limit for K values, and confidence level it corresponds to. Lastly, the unknown concentration. To find the concentration of the unknown sample and the standard deviation of it in both problems. So what will be our procedure? In order to arrive at a data and solve the problem, first, we will be computing the mean absorbance values or emission intensities and standard deviation of the values. Next, we will be looking and graphing the least squares best line through points given, calculating the calibration sensitivity and analytical sensitivity. Next, we will be calculating for the detection limit for a given K value and identify which confidence level it corresponds to. Lastly, we will be finding the concentration of unknown, computing for the unknown concentration and the standard deviation in the concentration. Now we would be going to our first problem. Here's the table of the data presented. For the first problem, it is the determination of zinc in multivitamin tablets using atomic absorption results. By the way, these two problems are included in the topic atomic absorption spectroscopy. The first problem, the following atomic absorption results were obtained for determinations of zinc and multivitamin tablets. All absorbance values are corrected for the appropriate reagent blank, with the concentration of zinc at 0.0. The mean value for the blank was 0.0000 with a standard deviation of 0.0047 absorbance units. We will be computing for A, find the mean absorbance values for the 5 and 10 standards and for the tablet sample. Find the standard deviation of these values. Next, find the least squares best line through the points at concentration of 0.0, 5.0, 10.0. Find the calibration sensitivity and analytical sensitivity. Find detection limit for a K value of 3. To what level of confidence does this correspond? Lastly, find the concentration of zinc in the tablet sample and the standard deviation in the concentration. Next, the calculations for the first problem. So here are the mean of the concentrations from 5 to the sample and the standard deviation from 5 to the sample. We use the formula for mean and the formula for the standard deviation. We arrived at 0.0489 for the 5 standard, 0.09793 for the 10 standard, 0.0649 for the unknown sample. For the standard deviation, 0.002821347 for the 5, 0.054000309 for the 10, and 0.003080584 for the sample. Next part, the least squares best line true points 0, 5, 10, calibration sensitivity, and analytical sensitivity. So before that, we will be computing for the S sub xx, X sub yy, and X sub xy that we will be using for the slope, intercept, calibration sensitivity, and analytical sensitivity. We use the least squares method here and the following formulas to arrive at the values. For the S sub xx, we achieve the value of 50. For the S sub y, we achieve the value of 0.0047951452267. For the S sub xy, we computed 0.48965. For the slope, we divided the S sub xy and to the S sub xx, arriving at the slope of 0.009793. Now we will use this slope to compute for the intercept through the slope-intercept formula or equation. So we substituted the slope, the mean of y and x values, and we arrived at negative 2.2 times 10 to the negative 5 intercept. Next part of our calculations for the first problem. Now we will use the values of the slope and the intercept to get the least squares equation. Now we arrived at the least squares equation of y equal to 0.0098x minus 0.00002. The calibration sensitivity is equal to the slope, which is 0.0098. The analytical sensitivity would be equal to slope divided by the standard deviation of the measurement. So we arrive at the analytical sensitivity of 3.47. So here's the graph of the determination of zinc in multivitamin tablets using atomic absorption results. For the X values, these are the concentrations of the zinc. For the Y values, these are the mean of the absorbance values. The next part for our first problem calculation is the detection limits. So we computed the detection limits as 3.47. For the last part of our first problem calculations, we computed for the concentration of the unknown by substituting the mean of the sample, the absorbance values of the sample, to the least squares equation. So we arrived at the concentration of the unknown as 6.629, and the standard deviation of the unknown as 0.0047 with the formula in the least squares method. Next, for the Excel spreadsheet, we tabulated the values of the X as concentrations of the zinc, including the unknown concentration of the sample, the values of Y as the mean of the absorbance values. So we computed for the slope, intercept, standard error count, the mean of the absorbance values, calibration sensitivity, analytical sensitivity, determination limit, concentration of the unknown, and the standard deviation of the unknown, using the given formulas here in the annotations and arrive at the same values in the calculations that we made in the least squares method. Last part of our first problem calculations, the graph, is the graph the determination of zinc in multivitamin tablets using atomic absorption results. You can see here, again, I will reiterate it, that the x values are the concentrations of zinc, and the mean of the absorbance values is the y values. So we can see here, this is very close to the line. It's almost exactly at the line, the values, the data of the first problem, and the r squared value of 1, exactly 1. For the next problem is the determination of sodium in blood serum sample using atomic emission measurements. This table again shows the concentration, but here we have the emission intensity, atomic emission measurements. So for the second problem, atomic emission measurements were made to determine sodium in a blood serum sample. The following emission intensities were obtained for standards of 5 and 10. And for the serum sample, all emission intensities were corrected for any blank emission. The mean value for the blank intensity concentration of sodium is 0.0, was 0.000, with a standard deviation of 0.0071 arbitrary units. So for our statistical data, we will find the mean emission intensity values for 5 and 10 standards and for the serum sample. Find the standard deviation of these values. B. Find the least squares best line. Prove the points at concentration of the sodium 0.01, 0.0, 5.0, 10.0. Find the calibration sensitivity and analytical sensitivity. C. Find the detection limit for K values of 2 and 3. To what level of confidence do these correspond? D. Find the concentration of sodium in the serum sample and standard deviation of the equation. First part, the calculations for the second problem. This is just the same as the first problem. We use the formulas for mean and the standard deviation and arrive at the following values of the mean of the concentration: 0.493, 1.003, 0.753. For the standard deviation, you can see here that concentration 5 and 10 has the same standard deviation of 0.0152, 75252, and the standard deviation of the sample is 0.037859389. Part of the calculations for the second problem, we again use the least squares method. So the s sub xx, x sub yy, and x sub xy. So we calculated for the slope and arrived at 0.100333. Next, we use the slope intercept formula or equation and substituted the mean, the slope and the mean of the x values and y values, and arrived at the slope and arrived at the intercept of negative 0.00278. For the least squares equation of the second problem, we substituted the value of the slope and the intercept that were calculated previously. So the least squares equation of the second problem is y is equal to 0.1003x minus 0.0028. Calibration sensitivity is equal to slope with calibration sensitivity is equal to 0.1003. The analytical sensitivity is equal to the slope over the standard deviation of the measurement. Our analytical sensitivity is equal to 6.57. So here's the graph of the second problem, the x values, concentrations, and the y values, the mean of the emission intensities for each concentration. Again, it is very clear that we can see that the data or the points are somewhat exactly to the line, and our r squared value is equal to 0.9999, which is somewhat similar to our first problem, which is r squared is equal to 1, exactly 1. Now we will proceed to the next part of the calculation for the second problem, the detection limit for the k values of 2 and 3. We use the formula for the detection limit. Now we arrive at 0.141528 at 92.1% confidence interval for the k value of 2 and 0.212292 at 98.3% confidence interval for the k value of. Last part of the calculations for the second problem, we substituted the mean for the emission intensities to the least squares equation to find the concentration of the unknown. The mean of the emission intensities for the sample, the intercept, and the slope, and arrive at the concentration of 7.54. And the standard deviation, we use the formula in the least squares method and arrive at the standard deviation of the unknown as 0.060477. For the Excel spreadsheet of the second problem, we also tabulated the x and y values, the x values as concentrations, y values as the mean of the emission intensities. We also computed for the standard deviation. We also, all these statistical tools or unknowns were calculated with the given formulas in the annotations and arrived at the same values that were computed using the least squares method presented earlier. For the last part of our second problem is the graph. So again, I will reiterate that the concentration of the sodium is the x values and the y values are the mean of the emission intensities, and our r squared value is equal to 0.9999, and our least squares equation is our least square best line. Now for the results and analysis of the two problems, here we can see the means. They are somewhat close to each other with the same significant figures. Standard deviation are relatively low. The least squares equation were calculated. The r squared values are somewhat similar, close, very close. The calibration sensitivity and the analytical sensitivity. Next are detection limits for the k values of 3, k values of 2, k values of 3. 1.44 at 98.3% confidence interval for the first problem. At a k value of 2, 0.14 at 92.1% confidence interval. K value of 3, 0.21 at 98.3% confidence interval. The concentration of the unknown was computed, presented earlier, 6.63 for the first problem and 7.54 for the second problem. The standard error was also computed and presented earlier. And this will be used for the final concentration, the interval, So the concentration of the sample is 6.63 plus or minus 0.005, and for the sodium 7.54 plus or minus 0.06. They both have a low interval. The table that was presented earlier shows the mean of both problems for 5, 10, and the sample are somewhat close to each other. The calculated standard deviation for all the samples were also relatively low. Both least squares equation were computed and are shown beside here, the least squares equation and the R squared values for both problems, which they show the linearity. So here the linearity. The calibration sensitivity were also obtained having 0.0098 and 0.1003 for first problem and second problem respectively. Analytical sensitivity was computed by dividing the slope to the standard deviation of the measurement, achieving 3.47 and 6.57 for the first problem and second problem respectively. The detection limit for the first problem at k-value 3 is 1.44 at 98.3% confidence interval. The determination limit for the second problem at k-value 2 is 0.14 at 92.1% confidence interval, and at k-value of 3 is 0.21 at 98.3% confidence interval. The final concentration for the unknown sample in both problems are 6.63 plus or minus 0.005 and 7.54 plus or minus 0.06 for first and second problem respectively. Both concentrations have low interval and high accuracy. For our conclusions, were the objectives met? The objectives of the problems is to identify the relationship of the values, compute for the different statistical tools, and identify the unknown concentration of the sample. The concentrations of zinc is at the X value, while the absorbance values and emission intensities serves as the Y value for the least squares method. The relationship between the values show linearity and R squared values that are accurate and acceptable. Different statistical tools were used and values were calculated. Finally, the concentrations for the sample were computed and arrived at the values of 6.63 plus or minus 0.005 and for the zinc concentration and 7.54 for the sodium concentrations. That was all. Thank you and God bless.